Hello, my name is Quinten, and today I will be talking about fully characterizing lossy catalytic computing. Let's introduce the notion of catalytic computing. Catalytic computing is a space-bounded model of computation, where we're given access to our normal space, but now we're also allowed to borrow some space that already contains information stored on it, do anything we want with it, as long as at the end of the computation we return it in its original form. One might imagine, for example, that one is doing an important calculation, but and one runs out of space. But somewhere one has a big database of important childhood memories and so on, things that one might want to keep, but only really accesses very, very rarely. Then, during the important calculation, we might change it and manipulate it, but at the end of the calculation, we do want it to return to its original form. That is catalytic computing. Catalytic computing is of interest because it is conceptually nice, but also some people believe it can be used to help understand the de-randomization of BPL, and it also can be interpreted as a way of amortizing space. Formally, catalytic computing is defined using Turing machines. In fact, catalytic computing is defined using a so-called catalytic Turing machine. Just as any normal Turing machine, a catalytic Turing machine has an input tape of length n, a work tape of length s, but now it is given additional access to a catalytic tape of length c. The work tape starts in the all-zero state, the input tape contains the input data, but the catalytic tape starts in an arbitrary state. Then, during the computation, the catalytic Turing machine can do anything it wants with both the workspace tape and the catalytic tape, but at the end of the computation, the catalytic tape must be returned to its original state. The main difference between the work tape and the catalytic tape being that the catalytic tape can start in any state and must be returned in its original state, whereas the work tape always starts in the all-zero state. This is called, or the complexity class corresponding to this model is called C space of S and C, where S is the length of the work tape and C is the length of the catalytic tape. Often we assume that the catalytic tape is exponentially longer than the work tape, and the standard parameters that we examine are the case where the work tape is logarithmic in length and the catalytic tape is polynomial in length, which is exponential in the work tape. Polynomial in the input tape, that is. Having defined catalytic computing, and in particular catalytic log space, CL, let's see where it fits into the complexity theoretic hierarchy. The trivial bounds on CL are L and P space. L because a catalytic log space machine that has no catalytic tape has only a logarithmically large clean space, which is exactly L. P space because a P space machine is just a catalytic log space machine where we're promised that the catalytic tape starts in the all-zero state. This gives us the trivial bounds on CL. However, perhaps surprisingly, better bounds can be found. In particular, it can be shown that BPL and NL are contained in CL. Furthermore, CL can be shown to be contained in ZPP. ZPP is conjectured to be equal to P. Both of these bounds seem to be stronger than the trivial bounds. ZPP is often assumed to be significantly smaller than P space, and BPL and NL are often assumed to be larger than L. We can do slightly better and show that even the determinant is contained in CL. These results are in some ways surprising, since the original goal of defining CL was to show that CL is no better than L, that borrowing space is not helpful. Nevertheless, the original authors found that CL appears, at least on first glance, to be significantly stronger than L. But our paper is not about catalytic computing. Our paper is about lossy catalytic computing. So what is that? Lossy catalytic computing is defined similarly to catalytic computing. We have 3 tapes, and we can perform a computation on these. However, unlike catalytic computing, we may not return our catalytic tape perfectly in its original state. We may return it with some errors, or some bit flips compared to the original state. We call the corresponding complexity class LC space. And again, S is typically logarithmic, and C is typically exponential in S. But now E might take a variety of different forms. So what is our contribution? Earlier this year, it was found that a constant number of errors do not change the power of catalytic computing. In particular, LC space with a constant number of errors is equal to C space, or LC space with no errors. We generalize this result to an arbitrary number of errors. In particular, we find that allowing E errors is equivalent to allowing E log C additional bits of clean space. One may think about this in many ways, but perhaps the most significant part is that errors are not a new independent currency of computation, as one might expect. Instead, errors somehow are just another form of space, at least in this model. It is important that we have some restrictions on the parameters. For example, we require that C is no more than exponential in S. Also, and another effect of this result is that, perhaps surprisingly, a non-constant number of errors, even a very, very small number of errors, as long as it's not constant, is likely to produce a class strictly more powerful than CL. We don't have an exact equivalent of a space hierarchy theorem here, but we do think that if we allow that, since that allowing more clean space is likely to produce a different complexity class. Our technique is also sufficiently robust that the result extends to BPCL and NCL, which are the bounded probabilistic and non-deterministic variants of CL. Let's describe how we prove this. Our result shows an equivalence of 2 different complexity classes, and as such, the standard approach to prove this is to show an inclusion in 2 directions. We will start by showing that LC space with E errors can be simulated in C space with more clean space. One may interpret this as showing that E errors can always be corrected using E log C clean space, additional clean space. Afterwards, we will show the other direction, which is to show that E errors can always be used to simulate E log C clean space. But we start by showing that E errors can be corrected in E log C with E log C space. So how do we correct errors using additional space? First, we have our standard catalytic Turing machine. And now we add the additional clean space to our machine. But we think of this clean space, these E log C extra bits, as being in fact parts of the catalytic tape. We do this because ideally we would like to use an error correcting code, but in order to correct a member of error correcting code, we need to ensure that we start with a code word. By adding log C additional bits, we can ensure that the catalytic tape, no matter what initial state it starts in, together when interpreted as a single bit piece of a single word together with the clean space, can always be turned into a code word. This allows us to assume without loss of generality that the catalytic tape is always a code word. And from there, we can start our error correcting procedure. In particular, we take our catalytic machine with the catalytic tape now extended to form a code word. We perform our computation. We end with some errors. But now, since we know we started in a code word, we are able to correct those errors using the error correcting code. It is important that our error correcting code can be corrected in a very little space, and we verify that. The error correcting codes we find most useful for our purpose are BCH codes with prime power fields. This completes the first direction of the proof. Now we move on to the second direction, which is to show that errors can simulate log C space. As one may imagine, in order to simulate log C bits using errors, it is sufficient to simulate log C bits using one error and then to repeat this approach several times. This is precisely what we do. In order to do this, what we need somehow is a method to allow a single bit flip to represent or log C bits, or to manipulate really log C bits. In order to do this, we define the following map, mem of x. Mem of x takes a length C bit string and tells us, the log C bit string that is really represented, but can at the same time be manipulated completely using single bit flips. That is to say that the output of log mem of x is a log C bit string that is represented, and it has the property that a single bit flip on the original string, as one sees on the right hand side here, can be turned into any manipulation on the represented string. A single bit flip here is represented as adding in binary a string of all zeros except at one position, and any manipulation is represented as adding any string, but now any log C bit string on the result. So let's see what mem of x is and how we use it. X is any binary string. And mem of x, in order to allow us to manipulate any binary string of length log C using single bit flips, we want mem of x to somehow have access to every possible manipulation. We do this by making mem of x a linear combination, or the inner product of x and all possible log C bit strings. In this case, we get the following sum. This has the property that if we want to just make a change, let's say we want to make a flip every bit once, then we can represent this by a single bit flip on the original string as such. Since every possible log C bit string shows up in the linear combination, there's always a single bit flip corresponding to any desired change in the output, in the hidden data. In this particular example, it is adding the bit string, or it's the single bit flip in the last position. We are now able to freely manipulate log C bits using a single bit flip on a length C bit string. So how do we use this to represent log C bits of free space using a single error? Our basic approach is the following. Our function mem of x in effect creates what we might call a virtual space. A virtual space of length log C bits corresponding to real data of length C. Our first step is to reset the virtual space to the all zero state, otherwise we cannot use it. Then we use this virtual space as we might in any computation, manipulating it using the techniques and the properties of mem of x. Finally, we reset the virtual space to the all zero state, and since we've reset it to the all virtual space, if we do this carefully, we can ensure that we end up in the same state we started in after resetting to all zeros. That means that we are now one bit flip away from the original state. This technique together allows us to simulate log C bits of clean space using one error. So how do we reset the virtual space? We're given an arbitrary catalytic state and correspondingly an arbitrary virtual space state. Our first step is to compute mem of the catalytic state into the clean space. From there, we can identify the single bit flip that will reset the virtual state space to 0. Having done so, we clean up the clean space to 0, and now we are ready for the computation to proceed. Notice that the only step where we really lose information here is when we reset the clean space to 0. Until then, we are in fact able to recover the original catalytic state. Afterwards, though, we are no longer able to do so. This completes the resetting or the initialization of the virtual space. So how do we manipulate the virtual space? As one might expect, we use the properties of memx to find single bit flips that correspond to transformations of the virtual space. However, we face one important caveat. We want only one bit flip to occur overall by the end of the computation. In order to do so, we need to ensure that the catalytic state corresponding to the virtual zero string at the start of the computation is the same as the catalytic state corresponding to the zero state that we achieve at the end of the computation. A simple method ensures that this happens. What we do is we ensure that even as we manipulate the virtual space, we only flip one bit of the virtual space at a time. In the example below, in order to change to the 101 state from the 000 state, we first flip the last bit and then flip the first bit. This involves 2 bit flips, but by doing them separately, we ensure that we always perform exactly the same bit flip for every change of the virtual space we perform. The result is that when we reach the final virtual zero state, we are in exactly the same catalytic state as the catalytic state we started in. This completes the explanation of how we use the virtual space. Finally, we need to reset once more to the alt zero state. So how do we reset to the virtual zero state? We do not use the same approach we used to reach the virtual zero state when we first turned the catalytic tape into the virtual zero state. The reason being that we need to ensure that we end up in the same catalytic state corresponding to virtual zero as we started with, and that means we are subjected to the same constraints as when we use the catalytic or the virtual space, which means we can only change one bit of the virtual space at a time. In particular, we do the following. We read out the virtual state space and put it in the workspace. Then we find what string we have and we reset one bit at a time to the virtual zero state. In the 101 case, we first reset the last bit, so the 001 bit, and then reset the 100 bit. These transformations are always the same, regardless of the state of the catalytic tape, and that means that as long as we adhere to these principles throughout the entire calculation in the virtual space, we have now successfully reset the virtual space to the same virtual space that we started, or same catalytic state that we started with, except for the 1-bit flip. This completes the resetting of the virtual space. We have now shown our result for a single error, meaning that when e equals 1, we can show that we can simulate log c bits of clean space. That is almost the result we want, but we need to prove that we can do the same for e errors. The extension to e errors is straightforward. We split our clean space into e blocks and similarly split our catalytic space into e blocks, and we repeat the trick e times, or e plus 1, e times. This achieves our result, but it does increase the catalytic space required by a factor of e plus 1. But we can do better than this. By allowing slightly more errors and splitting the catalytic tape into smaller components, we can simulate more clean space. In particular, by cutting the catalytic tape in half and increasing the error by 1, we double the number of clean space bits we can simulate, but we only increase the number of errors by 1. Using this approach more than once, we find that we can remove the factor of e in the catalytic space growth and get overall at most a constant increase in the amount of catalytic space and the number of errors. It improves on the earlier result. That completes the proof of the other direction and shows that LC space with E errors can simulate C space with E log C clean space. That completes our characterization of lossy catalytic computing. Perhaps the main thing is that it is in a sense surprising that errors turn out to be very similar to clean space. A priori, one might assume that errors are, in fact, a different resource, a different quantity, somehow orthogonal to clean space when dealing with lossy catalytic computing. In fact, this result shows that errors are entirely equivalent to clean space. Another consequence is that assuming something of a space hierarchy theorem like result holds, a non-constant number of errors likely produces a different complexity class. Finally, although our characterization is relatively clean and leaves many questions, still does not leave that many questions, we are interested in a quantum version, which we are still investigating. Thank you for your time.